Hello everyone, I'm Walter Poleman from UVM's Rubenstein School of Environment and Natural Resources, and today we're at one of UVM's 10 natural areas that are spread out through the state of Vermont. This one happens to be very close to campus. It's East Woods, a 40-acre parcel that is really in the middle of a fairly urbanized area of South Burlington. It's about 40 acres in size right now. It was actually twice that size when it was acquired by UVM back in 1949. But when the interstate highway went in, and particularly 189 went in, it cut right through the middle of the natural area. But still we have this preserved 40-acre area, which is an excellent habitat for wildlife and different natural community types, but also provides an excellent buffer for Potash Brook, which drains a large portion of the city of South Burlington as it flows through its watershed and makes its way down to Lake Champlain. In fact, if we focus in on the map here, you can see that really the 40 acres is sort of a postage stamp area within a larger developed watershed. Here's I-89 that I was talking about that cut through the middle of the forested area when it was first acquired. And this blue down here is where Potash Brook flows on its way to Shelburne Bay as it makes its way through. And so we're going to be taking a hike through the woods for a few minutes and working our way down to Potash Brook to really think about the water quality in the stream and how it reflects the surrounding land use of this area. All right, we just entered East Woods, heading down the trail to go meet my friend Chris down by Potash Brook. Well, we've walked in a little ways through the entrance to East Woods, and you'll notice that it's just a really flat, sandy terrace for the first few hundred meters. But pretty soon we come to this point where the steepness of the landscape and the rolling terrain kind of comes into focus as we work our way down to Potash Brook. Essentially, the sand here is all a remnant of the sandy delta where the ancient Winooski River flowed into the Champlain Sea. All right, we're about halfway down to Potash Brook, but along our way, there's this really interesting landform in here. You can see this whole kind of hollow in here, extending through this way, through the sand, and as we go out this direction, you can see the landform actually comes to an abrupt halt here. And as you study the history of East Woods, you would know that way back in the 1890s, they were going to build a railroad actually connecting Burlington to sort of the areas further out, and this is where the railroad bed was going to be. And essentially right here, a bridge abutment was going to be built across Potash Brook to the other side, but right now it's pretty much the bridge to nowhere because it ends abruptly right here. But just some of the past legacy and land use history of East Woods. It's got a rich glacial history, with all this sand deposits here from the glacial lakes, but also a human history that belies the facts about the development of this as an urban area way back 100 years ago. All right, Chris is down there somewhere along Potash Brook. Let's go find him.
Hello, Chris Brooks here with the Rubenstein School for Environment and Natural Resources, and today we are down here at Potash Brook in East Woods, which is part of the university's natural area system that the university manages. And we're here today really looking at the stream dynamics and the ecology of this stream. Potash Brook is actually an impaired waterway. Today, it is not meeting water quality standards for stormwater inputs. It's not meeting water quality standards for bacteria or E. coli. And really what's driving the morphology of this stream and driving the water quality issues down here is all of the developed lands that surround East Woods and Potash Brook in this watershed. It's a roughly 7.5 square mile watershed. And in terms of land cover, almost 19% of it is impervious surfaces. Buildings, rooftops, roadways, create a tremendous amount of impervious surface in this watershed, and that's driving water quality issues down here in the brook. So all of the stormwater inputs that are created by that impervious surface bring pollutants down into this watershed. So sediment, phosphorus, metals, all sorts of various organic compounds, oils, bacteria is entering the woods primarily from all of this stormwater. There's also bacteria getting into the stream, potentially from leaky sanitary sewer pipes, from failing septic systems in the South Burlington area, or even animal waste from individual homeowners' lawns. So really, the name of the game in terms of managing an urbanized watershed is all about incorporating green stormwater infrastructure throughout the watershed. Things like gravel wetlands, permeable pavements, rain gardens, and there's even a host of things that individual landowners can do on their property to incorporate green stormwater infrastructure. Thinking about green roofs, rain barrels, incorporating little rain gardens in your yard. All of this green stormwater infrastructure has the same goal or purpose, which is to mimic natural systems, to mimic the hydrology of this system as though there weren't any impervious surfaces here. So green stormwater infrastructure helps to slow down stormwater flow, helps to filter out pollutants before it enters the stream down here, and ultimately it's mimicking the natural processes as though rain were falling in the woods here. So water's allowed to percolate slowly down to the water table and slowly enter the stream, as opposed to being channelized in a culvert or a pipe and shot straight into the watershed. So there's two things. There's pollutants being brought down here from all the stormwater. The stormwater inputs also simply increase the flow of water through Potash Brook during high rain events. So even though we've got a nice vegetated riparian buffer here, you can tell that there's still erosion going on during high rain events because of all the stormwater. The management strategy here is about green infrastructure, and the City of Burlington and the City of South Burlington have increasingly invested in green stormwater infrastructure projects to protect the health of Potash Brook and ultimately the health of Lake Champlain, because everything that's entering Potash Brook is ultimately dumping into the lake.
I'm really pleased that I'm here today with Ashley Eaton. And Ashley works for Lake Champlain Sea Grant, and she's going to tell us a little bit about her organization and what they do down here at Potash Brook. So Ashley, can you tell us a little bit about your organization?
So Sea Grant is a national program funded through NOAA, the National Oceanic and Atmospheric Administration. There are 33 programs throughout the United States as well as in Puerto Rico and Guam. Basically, the goal of Sea Grant overall is to solve local water quality problems. So to be really rooted in the community and really in touch with what's happening in those ecosystems so that you can create relevant and responsive programming, research, and education. And so at Lake Champlain Sea Grant, we're focused on the Lake Champlain watershed, which entails the Vermont portion, as well as the New York portion and a teeny bit of Quebec. And so my role at Lake Champlain Sea Grant as the Watershed and Lake Education Coordinator is to facilitate a program called Watershed Alliance. My role really is to oversee our K-12 undergraduate and teacher professional development programming. Our goal is to get students out into the field and involved in place-based science, so evaluating waterways, whether it's streams or lakes. We work with undergraduate students who actually facilitate our programs. Oftentimes they're interns from the University of Vermont. And then we also provide professional development training to K-12 teachers that are interested in integrating watershed science into their curriculum. Additionally, we provide programming in the Rubenstein Ecosystem Science Laboratory and aboard the research vessel Melisira.
Wonderful. With the Watershed Alliance being involved in community science and monitoring, how do you work with teachers and students?
Yeah, so our program provides kind of three core programs. One is stream monitoring, which I mentioned. The other is Keeping the Balance, which is a lab-based program. So that happens at the Rubenstein Ecosystem Sciences Lab and is a dissection for students. And then our third is aboard the RV Melisira. We take students out and explore basic limnology and lake science. So kind of the research that's happening as well as some of the ecosystems. Our programming is facilitated by undergraduate students, oftentimes from the University of Vermont, that are interning as watershed educators. They oftentimes have an interest in environmental education or environmental science and are just looking to get some kind of hands-on time in the field working with students and working with monitoring equipment.
So we're here at Potash Brook. What makes this such a unique place for stream monitoring?
Yeah, this is a really unique ecosystem here at Potash Brook. So this is in the greater Burlington area in South Burlington. And our monitoring program is about 20 years old, and this was actually one of the first sites that we started monitoring with students. It is an urban stream, despite the scenery that you're seeing here today. And this stream is impaired for stormwater, and then on the lower section, actually some biological impairments like bacteria. And this stream is really unique because of its surrounding area and the region that it passes through. So you're getting a lot of stormwater runoff to this stream reach right here, which has a significant impact on the ecosystem.
In terms of testing the health of the stream, what are the actual elements involved in stream monitoring?
Yeah, so in our program, we focus on 3 facets: biological, chemical, and physical monitoring. And then we kind of break each of those down into a variety of subsets. And we're really trying to find quantifiable metrics that we can measure and track over time. So when we are coming to a stream like Potash and we're evaluating for biological indicators, we're really measuring biological components such as benthic macroinvertebrates. Those organisms are going to be really phenomenal indicators of water quality based on the fact that they are here for a long duration of time. They spend their life, if not all of their life cycle, here in the stream, and they're going to tell us important things about dissolved oxygen. They're going to tell us about pollutants that are maybe coming in through stormwater. And so the tolerance of the organisms that we find here in the stream will help us kind of draw a connection to the greater water quality. All right, so I'm going to go right below this riffle here, this little spot where you can see some of these bubbles. That's an indicator that there's a lot of dissolved oxygen. So I'm just going to get the net kind of on the bottom of the stream here. All right, there's a couple little things in there.
Ashley, now that you've collected some of these macroinvertebrates using your D-net in the stream, how do you go about sort of determining what they can tell us about water quality?
So after we've kind of collected our sample, kicking around the stream for a couple minutes, it's nice to kind of spread it out in a white tray like this so you can actually see what is happening inside the sample. We're going to be able to start kind of identifying individual organisms, and then we're going to start just grouping them together. We're just going to start by putting organisms that look like similar organisms together, and that's going to help us when we get to the end in classifying the organisms we have and then identifying kind of where they sit and how they are indicators of pollution tolerance based on their identification. So I'm going to start trying to select out some organisms from our sample. Something that I'm looking for, there are 3 species that are really intolerant of pollution, and those are caddisflies, mayflies, and stoneflies. So just from initial observation, if I'm seeing a lot of those organisms in this sample, that's going to tell me that the water quality in the stream is actually probably pretty great. It also tells me that there are high levels of dissolved oxygen, so thinking back to the chemical monitoring station. And so let's see what we can find in here. So we have our first organism, which is going to be a stonefly. Something that's also really interesting to think about is time of year. So even though this is fall, there are organisms, benthic macroinvertebrates, living in the stream all year round, some of which will spend their entire life cycle living underwater. Others will actually spend part of their life cycle and then hatch and emerge. That would be an organism like a dragonfly. So let's see what else we can find. Oh, yes, okay. All right, here we go. There's a good one. Dobson fly, I think. It's hidden, but... And so something else that's really interesting as we start looking at these organisms, they all have really distinguishing characteristics. And there are kind of two key features that you can note. You can note how flat the body is. So these organisms live on the bottom of the stream, and so that's an adaptation that's going to help them cling to rocks in that benthic zone on the bottom. Additionally, you will start to see some other kind of interesting things like appendages or other kind of characteristics. And another question to ask yourself is, how are these organisms taking dissolved oxygen out of the water? And so on the stonefly we have here, you can they often have gills, depending on the species, in their armpits, and that's actually going to help them basically pass water over and take in dissolved oxygen. So when we start to look at species that are more tolerant of pollution, they have heavier adaptations basically to take dissolved oxygen out of the water, because oftentimes in those systems they are lower dissolved oxygen and a bit more impaired. Great. Two of the other components are physical monitoring as well as chemical monitoring. So in terms of chemical monitoring, one of the pieces that we often focus on is dissolved oxygen. Dissolved oxygen is a really important chemical parameter because it tells us how much oxygen is present in the water column for the biological organisms that are living in the ecosystem. And so this can kind of help us determine what might be able to survive or thrive in this environment. For the monitoring that we do when we're testing dissolved oxygen, we're using this base level Hawk kit. This is going to give us a great baseline reading in milligrams per liter in the amount of dissolved oxygen that's in the stream, in the spot that we're sampling and at the time that we're sampling. And as I mentioned earlier, dissolved oxygen is really essential for those biological organisms like benthics. And so this is going to tell us kind of about the habitat and if they're able to survive and thrive in this ecosystem. Inside the kit, we have basically a series of reagents that we're going to add. And the vial that we're going to measure this in is specifically designed so that we are able to basically eliminate any atmospheric oxygen, which is really important. Another key element to monitoring dissolved oxygen is doing it pretty rapidly. So dissolved oxygen actually changes depending on the temperature of the water. So depending on the temperature, so if we were to take this from a really cool stream today and then bring it back to the lab, by the time we were monitoring that, it would be pretty inaccurate. So this stream-side sampling kit has a series of reagents that we'll add. They are going to basically work to kind of bind the oxygen in a way that we can measure it. And then for those of you that remember from chemistry, this actually ends in a titration, and that titration is going to allow us to actually get a specific number of milligrams per liter.
Ashley, in terms of measuring dissolved oxygen, what's the range of readings that you might expect in a stream?
Yeah, that's a great question. So when we look at benthic organisms, we're really looking at a specific range. So we really want it to be kind of above 7 milligrams per liter, and that's going to be on the lower end for organisms. And then as you start to increase and see 10, 11, 12 milligrams per liter, you are basically going to have optimum life for any organism that you might be sampling. So when you're done stream monitoring, you end up with a picture that has information on the biological systems, the chemical analysis, as well as the physical kind of attributes of the stream system. Together, those weave a really great story about what's happening in that place, and it tells you a lot about what's happening on the landscape as well, not only what's happening specifically in the stream when you're there monitoring on that day. Additionally, we might measure things like pH, orthophosphates. When it comes to physical monitoring, that's really an assessment of the landscape. So we're assessing not only what's happening here in the stream, but we're also looking around and evaluating what's happening in the surrounding area, such as the floodplain, the riparian zone, and taking some measurements to kind of calculate that as well.
As you say, you've been monitoring this place for the last 20 years. What trends in stream health have you noticed?
Yeah, so actually we use this stream kind of as a quirky little zebra stream, so it's not what you would expect. We bring students here, and oftentimes they think because this is in an urban area, they're expecting to see great impairment, especially with the biological indicators, but that actually isn't necessarily what you'll find. There actually are really diverse communities of organisms living here despite kind of the stormwater impairment, which is really interesting.
So sometimes the local habitat for these benthic invertebrates is perhaps even as important as the watershed context.
Yeah, I think there's a lot of really complex factors when it comes to ecosystems and their dynamic nature. So I think even though there are impairments from stormwater, there definitely is an ecosystem resilience that's happening here in the biological community.
Right. I know the headwaters of this stream are up to the east of here as you move towards the foothills of the Green Mountains. But where does this brook end up?
Great question. Yeah, so We are on the lower section of Potash Brook, actually just beyond the road that you can't see here is basically the mouth of the river. So it's actually going to open up to Lake Champlain. This lower section, you can kind of take cues from the landscape here that this is, not a headwater section based on the cobble that we're seeing and kind of the surrounding area. So this is eventually just going to end up in Lake Champlain.
In terms of the community of South Burlington and what they're doing to steward the water quality here, do you know of any good examples in South Burlington in terms of this idea of stormwater infrastructure or how they're working with water quality on the landscape?
Yeah, so one great example, one of my colleagues actually was working on a research project with South Burlington Public Works, and they were working on a green stormwater infrastructure and doing some research on a floating treatment wetland in a community in South Burlington. And so that is one way to take and adopt infrastructure that's already installed, like a bioretention area, like a stormwater pond, and actually retrofit it with something that may potentially be more advantageous in reducing phosphorus or nitrogen or other nutrient elements that might be in the water.
Ashley, thanks so much.
All right, thanks everyone.